Hello everyone, how are you doing? I hope you are doing well. Welcome to this video. This is the video part number 3 from the test-driven development episode. If you didn't watch the video part number 2, you should watch it as first and then watch this video. Okay, what's on the agenda in this video? Today we are going to add a new feature to the add function that we have written in the last sessions. What's the new feature? The add function should accept several parameters like this. As you see, we can give several parameters to the add function. It could be 2 parameters or 3, 4, 5, as much as you need. Okay, how can we implement it in C++? Actually, there are 2 ways to do that. The first one is the Varargs, which you may have seen in C language also. You can see how we can use Varargs in this example. But it's not a good way. Do you know why? Okay, I leave it to Peter Sommerlad. He will tell you why it's not a good way.
So what are we talking about? And anybody here has written a function taking C-style Varargs yet in his life? Wow. Who found it nice and convenient to implement it? Okay. I claim Varargs suck. And we all learned this morning from Bjarne that he wants to C++ be a type-safe language, and Varargs are inherently type unsafe. It's very hard to implement correctly, and on the other hand, it's completely unsafe because you have to specify the type and number of actual arguments in some means where the compiler has no control on it. Who has ever called printf wrong? You see, that's a problem. And this is a brain-dead simple example of printing numbers, but you have to either make sure that all your numbers have the same type, down here, int, or do it in the printf way where you implicitly specify the type and the number of arguments through another argument, the format string, which is very error-prone and hard to do right. Now let's see. Varargs sucks. And at least some of you can confirm that. And it's in the language because we still have the C legacy of printf and scanf. It's very error-prone. Just consider things outputting an int, but giving it a double. It's unchecked by compilers. Well, there are tools who check the format strings of printf and scanf, but they're not commonly used, and some compilers will complain, others not. It's very difficult to implement it yourself correctly, and we only get passed by value. When we want to do something by like scanf, or we want to have a side effect, we have to use pointers. And even Bjarne still loves pointers, plain pointers, to mean something. I hate pointers because they still mean the old way of doing things in C, and that's not very C++ish for me. And we even have a plugin for our IDE that is called Point Terminator. But only internally. We couldn't use that name officially, otherwise we get sued by Hollywood. So we learned that already. Number and types of arguments. So, come on. Shit. That's when you do too many animations.
You can type the slide number of the PowerPoint.
Let's see if that works. I want this slide. Thank you. Learned something. Okay, what we actually want to use functions, maybe printline is not a very good example, it's so Pascal-ish, but nevertheless, it's something we want to call a function where we just pass about anything, and if it works, it works, and if it doesn't work, we get a compile error. In Java, you get similar things, but even there, it's not really type safe because everything is passed as an object.
Okay, did you get that? Actually, CppCon is the best way to learn C++. The second way is the parameter pack in C++11. I leave it to Peter Sommerlad again to explain it to you how it works.
And in C++, since C++11, we have a nice feature called Variadic template. And that's actually what we want to do. Actually, even before C++11, people were struggling with providing functions with multiple overloads to simulate what variadic templates actually are about. So we have, for example, boost bind, that's in there since 2000 something, early 2000s, where we have a function binder where we can call a function or a functor with any number of arguments that actually that function takes, and that's fine and it works. We have even boost tuple where we can have arbitrary values of arbitrary types combined together in a single value. But to actually get that done requires a lot of repetitive code or using interesting macro features like the Boost preprocessor library provides to actually get that. And you always have a built-in maximum. You always have to specify, okay, I want bind with up to 10 arguments. That might be sufficient for almost all imaginable use cases, but somehow you might get a Windows API function with just 11 arguments. And we can argue a lot about the usefulness of such APIs, but it's still there. So what we would have done is actually provide print line overloads with any number and so on. So without any additional argument in addition to the stream, with a single one, 2, 3, and so on, to be able to call print line with any number of arguments. That's not very convenient, a lot of repetitive code, and easy to make copy-paste mistakes. So who of you actually successfully wrote a template function in his or her life? Okay. Who never has written a template function? Very, very, very few. So the key about templates and function templates is we have functions in C++, we have overload resolution, which is a very tricky part. And if you want to see what we do about get better overload resolution visualization, come tomorrow morning to my demo. And the key is we have pattern matching. So whenever you call a function, based on the type of the arguments and the number of the arguments, the corresponding function will be selected by the compiler by magic. And if there are template functions in the game, even their selection and instantiation happens more or less by magic. I don't want to go into the details, but there is kind of a best match situation that actually happens. And with class templates, we don't have overloads, we have specializations. So not only having a basic template for a class, we can have specializations either partially, like for pointers, pointer types, or complete specializations for specific combination of template arguments, and provide specific versions of an implementation for that specific case, or these cases. The classical example is vector bool. Who has ever used vector bool successfully? Without surprises? Okay, come to my demo tomorrow and see what happens with vector bool. So actually defining a variadic template function reuses a little bit of syntax, the ellipsis we already know from C, but in a more structured way. We have type name or other template arguments with a variable number of those, which can be 0 or more. We usually use, if we define a function, a variadic template function, these type name arguments to specify our function arguments. And then we can use these function arguments by expanding them with another expression or call where it just replaces all of the arguments. That gives us the syntax. So we have ellipsis in front of a name defining, okay, this is a so-called parameter pack. We have any number of these things. And if we use it after a name, it expands to how many actually are there when the function is called or the template is instantiated, and it's replaced by a list of these things. Now, this is not very useful yet, because how do we implement that? If we call the example Variadic with any number of arguments and then call out println in there, how do we implement println? And okay, I already told you the terminology. We have the parameter packs and the pack expansion. So how do we implement it? And the key to that is actually recursion. So who has written successfully any kind of recursive function in his life or her life? Okay, you're all experts now. The key to recursion is actually you have a base case, typically with a parameter pack size of 0. And you have the regular case where you just take one away and do something with that one and then call the function itself with the rest. And it should somehow, so we provide a base case for our println without any arguments, and this doesn't even have to need to be a template function, it's just a plain overload. And then we have an implementation where we actually spell out, okay, we have our stream to pass and we have the head, the tail, and now we do something with the head, outputting it on the stream. If there is still something in the tail, we just arbitrarily place a comma there and then call out for the rest of the elements into our println function. Whenever the last thing happens that the tail is actually empty, it's println with just out, and that we provide an overload for upfront without any arguments, and then the other println actually gets called. You could do that. It's not that hard. So, I'm done. Well, there are some interesting aspects about templates, Variadic templates and recursion. One of them is, okay, because it's a template, we always have to provide the whole source code. So we place the complete implementation in the header file. Not a big deal. But also, even if we never call the version of println where we actually have an empty tail, we must provide an overload for that situation. Why is that the case? You never call something, nevertheless, the compiler complains about that. And the situation is because the compiler sees the source code, instantiates println up until the tail gets smaller and smaller and smaller, and if we got just one element left, the tail is empty. So we call println with one argument, matches into the head, the tail is empty, size of tail is 0, but it still has to compile this little piece of code, even though it's not called when size of tail is 0. So we have to provide the overload with println and the 0 size parameter pack, so the println without anything, even though it's never called. So we have to provide this overload, and we get compile errors if we forget that.
Alright, you have learned how you can use parameter pack in C++. Let's implement the feature that I've told you at the beginning of this video. But before that, check out the session 3 branch, open up the Visual Studio Code, on a status bar, click on branch button, and then session 3. Okay, remember the TDD cycle. First of all, you should write a test case to demonstrate the new feature. Test f macro, test fixture name, and test case name. Add function should takes several parameters. You can copy the previous assertion and pass several parameters to the add function. Okay. Make sure the test case is failed. It's failed. Alright, the next step, get it to pass. Template, type name. This is the first template type for first argument, and the next one is the Variadic template parameters. First argument, and the next one is the Variadic parameters. As Peter said, a Variadic template function is based on recursion. You can implement it in this way. Alright, you're done. As Peter said, we should also implement the base case with 0 arguments to matches in the end. But we don't need to do that, because we have implemented the base case in the last sessions. Actually, this function signature is the base case for our new Variadic template function. Okay, run the test cases. Okay, you are done. All of the test cases are passed. The final step, clean up the design. Okay, I think we can move this module to its own header file. Create a new header file called math.h and move this module to its header file. And you can include it here. Run the test cases again. All of the test cases are passed. Alright, that's all for this video. We're coming to the end of this video, and I hope you enjoyed it. Thank you so much, and have a nice one.